The nice cool winter weather is pretty much coming to an end in Mumbai, but there is a bit of a breeze here, and I hope the sound is not getting too much of that sound, too much of that noise here. So let's continue with this buoyancy forcing. We were looking at the two trans or vertical profiles here at 25° west and 20 south and 25° west and 1.5 degree south. Here we are looking at zonal mean profiles of surface air density, sea surface density averaged over 2012 and 2014, and C is a map of sea surface density in kilograms per meter cube in the Atlantic sector for the same period. Sea surface density calculated using the equation of state, which is a fifth order polynomial of temperature and salinity based on observational sea surface temperatures and sea surface salinity from Aquarius and some other data set for temperature. The locations of two hydrographic sections we saw before are these, as I said. So if you go from minus 80 west to whatever 80 west here, you can see 80 east, I suspect. So we are going in the sorry, this is a latitudinal section. Yeah, so these are the zonal mean profiles in the meridional sense. So you have a high density in the Southern Ocean at 80 south, and density decreases as you come towards lower latitudes. You can see the lighter densities here in these bluish colors, heavier densities in these reddish colors. So density is decreasing towards the low latitudes, again increasing towards the high latitudes with some other small water masses that we will ignore for now. So the surface air density corresponds to the ocean. Where the ocean is warm, where the ocean is cold, surface air is heavy as well. Of course, orders of magnitude difference in the densities. This is 1.3 kilogram per meter cube here, and this is 1000 something kilograms per meter cube, which we already know. So warm moist air in the tropics rises, expands. This is basically our ITCZ, where we have freshwater flux and lighter densities, and there are also mixing of Amazon River here that we have to be careful about, and Orinoco River comes out here. Here Congo, Zaire and Niger rivers come out here, and so on and so forth, that affect the ocean density. So you can see that ocean density also is high in the low latitudes, but because of the dynamic reasons, the density increases towards the north here after the Antarctic bottom and intermediate waters are formed that sink to the subsurface, and surface densities are increasing towards here. So dense water sinks at high latitudes, and then seawater density drops, and under the ITCZ to the north of the equator you get the lightest waters, which we are seeing here, and then increases towards the high latitudes, and again at this latitude here we are getting the highest density where the North Atlantic deep water forms, and then you have again decreasing density towards the north. Okay, so this is the density flux, and as I said before, this is from Stefan Rahmstorff, who said in 2003 there are thus two distinct forcing mechanisms. So wind forcing and buoyancy forcing are definitely two forcings, but not two separate circulations. So even though we tend to think of wind-driven circulation and thermohaline circulation, they are not really two circulations. I can feel the wind, and I'll see how bad the sound is. Change the wind stress and the thermohaline circulation will change. Alter the thermohaline forcing and the wind currents will also change. It is because of the thermohaline forcing that wind-driven currents are relegated to the upper ocean. In unstratified water they would extend to the bottom. Okay, so something to remember. Chris says that the first global conveyor belt figure I saw is not the best one to show. He doesn't show that kind of a figure in his book because he says he doesn't like them, but I showed one anyways. But what he shows instead is this schematic illustration of the global thermohaline circulation with Antarctic-centered view of the interbasin flows, inspired by the diagram of Arnold Gordon and William Schmidt's. Watermass details are shown in the Atlantic sector, including the thermocline, intermediate water, North Atlantic deep water, Antarctic bottom water. The Antarctic circumpolar current ACC flows clockwise west to east around Antarctica, connecting the three major ocean basins which we saw before. The locations of the two hydrographic sections shown in figure 8.1 before are labeled on the top of the Atlantic sector, which is here, 20 south, 1.5 south, 25 west. So I tend to call the Southern Ocean as a mixing bowl because the North Atlantic deep water comes in, Antarctic bottom water, Antarctic intermediate water, and the surface waters all circulate around the Southern Ocean, and then there is the deep intermediate water inundating the Indian Ocean sector, which is close to the north, converted into surface water, driven southward to enter the ACC again in a complex way with Agulhas retroflexion and circulation around the southern tip of Africa into the North Atlantic as we saw before. There is a similar inundation of the deep and bottom waters, intermediate waters into the Pacific, which is a much bigger basin, into the North Pacific, getting converted to surface water, coming back into the Indian Ocean through the Indonesian seas and going back out into the Southern Ocean and the North Atlantic. The Atlantic Ocean is shown with some detail here, so you have the Antarctic bottom water that sinks to the bottom and inundates the Atlantic Ocean in addition to the Indian and Pacific Oceans. North Atlantic deep water is forced to pick its neutral buoyancy location. It's complicated circulation, but nonetheless we are made it look simple. And you have thermocline with the upwelling affecting the little dome here, and subtropical gyres where the convergence happens, creating the trough in the thermocline, and the hydrographic sections we saw before are here. So here is the northward cross-equatorial transport of salt and heat that feeds the sinking North Atlantic deep water formation, and you have the rest of the thermocline intermediate water occupying these regions here. So the North Atlantic deep water gets pulled up between the Antarctic intermediate water and the Antarctic bottom water by the divergence in the Southern Ocean. Okay, so obviously thermohaline circulation affects all properties of the ocean in the vertical as well, and the impact is seen very nicely here when we look at the dissolved oxygen in the water average for the North Pacific and North Atlantic. For example, you expect dissolved oxygen in the water to be high near the surface where photosynthesis exchange with the atmosphere happens, where the oxygen is very high, but you can see in the water it's fairly low compared to the atmosphere, so it's of the order of 8 milligrams per liter or so. Photosynthesis produces all the phytoplankton, a lot of feeders on it which sink, that matter sinks and then is respired, consumed by a lot of the species that live here, so they consume oxygen, and you can see there is an oxygen minimum zone produced here. But clearly the oxygen in the Atlantic is much higher than the oxygen in the North Pacific, because the deep water that's sinking brings high oxygen from near the surface to about 1 kilometer here, and it's higher all the way to the bottom because the sinking water has higher oxygen, and it is that high oxygen that is also bringing increasing oxygen with depth in the Pacific, because the thermohaline circulation is feeding that. So here the thermohaline circulation sinking water that is inundating the deeper ocean is also bringing oxygen with it from the southern ocean, which is clearly seen here. And there is of course corresponding profiles in nutrients like nitrate, which is consumed near the surface. Those hydrocarbons formed during photosynthesis fall down and are recycled, so there is nutrient being converted from organic matter into inorganic nitrate, so nitrate increases. As you can see, older waters of the Pacific then tend to have higher nitrate all the way down, whereas the nutrient poor photosynthesized organic matter sinking here decreases the nutrient profile in the Atlantic, which is like a mirror image of the oxygen profile that you can see here. Similarly, in CO2, you see that the Pacific old water has higher CO2 photosynthesis exchange with the atmosphere, produces low CO2 near the surface in micromoles per kilogram, and it increases because there is respiration. Consumption of oxygen is associated with increasing CO2. Cold, high pressure waters keep CO2 higher in the North Pacific. It's older water, whereas the low CO2 being brought down by the North Atlantic deepwater formation keeps the CO2 lower relative to Pacific in the North Atlantic. So obviously if you plot the pH, which is related to the acidity of the water, so high CO2 means high carbonic acid, so the pH will be lower for the Pacific compared to the Atlantic. So the profile will be the mirror image of this, with pH for Atlantic being higher than the Pacific. So all these things matter because with global warming we are trying to see how much heat and greenhouse gases are being taken up by the ocean. So we'll see that in the next chapter. Okay, so let's leave this here and then come back and look at thermohaline circulation in the past and touch a little on paleoclimate just to conclude this chapter. And as I said before, paleoclimate cannot be really discussed without considering the role of the thermohaline circulation, because on the long time scales, orbital time scales, the ocean's role in storing and releasing heat and greenhouse gases plays a big role on longer time scale climate variability, whereas now CO2 is playing role as a greenhouse gas in the atmosphere because we have increased it rapidly by fossil fuel burning. So we'll see, briefly touch on this a little bit in the next podcast. Okay.